Last video, we looked at the idea of momentum and conservation of momentum and impulse and all of those concepts. Today, what we're going to look at is just a quick example of how conservation of momentum can be useful. So, a sort of simple question that can be asked is you have two billiard balls, they come together and they collide. Ball A is moving at 2 meters per second in this direction prior to the collision and ball B is moving at 2 meters per second in this direction. They hit, ball A comes off at this speed in that direction. How fast is ball B, or what's the velocity of ball B after the collision, right? So what we know here is when we look at this collision, we have ball A and ball B. They come together, they interact. There's a forces that cause them both to accelerate and change direction. That force is just internal. It's between A and B. So if we define our system, our total system is both ball A and B, the only thing that's in there is an internal force between them. Newton's third law says that there's a force on A and a force on B that are equal and opposite. That's what led us to conservation of momentum. So we know if we define that as our system, that the total initial momentum is going to be equal to the total final momentum. And momentum, as we remember from last video, is a vector, right? So we can use this equation and really quickly, much more simply than using anything else we've learned in this semester, figure out the answer to this question and analyze this problem. These are vectors, so we have to do it component-wise, though. So we're going to look at the x components of momentum and then the y components of momentum. So the x components, initially we have ball A, which is the mass. All balls have the same mass in this case, times the velocity of ball A in the x direction initially. And then the same thing, but for ball B. And that's going to be equal to the mass of ball A in the x direction at the end, the final velocity in the x direction, plus the mass of ball B times the velocity of ball B in the x direction at the end. And right away, we have our equation that's going to describe the system, and we can use this to try and figure some things out. Now, we just kind of have to ask, well, what are these quantities? Well, already, just to make our lives simpler, because these masses are the same, we can divide everything by m and just cancel these out, right? Then we can sit here and say, well, what's the velocity of x in the y, the velocity of ball A in the x direction at the start? And all we have to do is, if our coordinate systems are standard x, y, we have to split this into components. It's got a VAX initial and a VAY initial, right? And if we want to figure this out, well, if this angle is our 30 degrees, the x component here, that side opposite that angle, that's going to be equal to V naught sine of that angle, right? If we remember our trig functions. V naught is the initial speed of that hypotenuse. So it's going to be 2 meters per second times sine of 30 degrees, and it's in the positive x direction. So this ends up being 2 meters per second times sine of 30 degrees. And what about our velocity b in the x direction? Well, this is entirely in the x direction. It's going 2 meters per second in the negative x direction. So this is just minus 2 meters per second, right? If we look at after the collision, the velocity of A after the collision is again not in x or y. It's got to be split up into components. So we have VAY final and VAX final. And if we're looking for VAX final, it is, again, opposite this angle, which happens to be 30 degrees as well. So the hypotenuse is 2 meters per second. This is going to be the same sort of thing, 2 meters per second times sine of 30 degrees. However, this is in the negative x direction now, so this is going to be negative, that speed, that velocity. And we're trying to figure out how ball B is moving after the collision. We don't know that. This is what we're going to try and find. So the velocity of ball B after the collision's there. We can now solve this, right? If we bring, this over to the other side, we have, 2 meters per second sine 30 degrees plus 2 meters per second times sine 30 degrees minus 2 meters per second equals VB x final. Well, if you enter this into your calculator and sort this all out, sine of 30 is 1 over 2, so this becomes 1 plus 1 minus 2. This is 0 meters per second is equal to V final of ball B in the x direction. Sorry. So we know left or right, this ball isn't moving left or right after the collision. In the x direction, it has no velocity. We can then do the same sort of thing with the y components of this ball, of these balls, and we have mass times VA in the y direction at the start plus mass VB in the y direction at the start. It's going to be equal to those final momentum, the mv for both of those balls in the y direction. And we do the same sort of thing. We have another equation here. We just have to think of what those components are. Just like previously, we can cancel out those masses and then just sort out what those components are. Well, in the y direction, we have this component here. It's just going to be V naught cosine theta. It's the side of that triangle adjacent to that angle. So, and it's going to be in the negative direction. It's pointed downwards. So this ends up being negative 2 meters per second cosine of 30. Y, the ball B has no component in the y direction. It's moving purely left to right. So that's 0. After the collision, ball A is again adjacent to that 30-degree angle. So it's going to be V naught cosine of that angle, and it's still going downwards, so that's a negative. So this is going to be negative 2 meters per second cosine 30 degrees. And that's going to also have the final speed in y. We don't know what that ball is doing after the collision yet. Again, we can figure this out. We can solve for our final speed in the y direction, or final velocity in the y direction of our ball. Bring this over, we end up with negative 2 meters per second cosine 30 plus this once we bring it over. So this also ends up being 0 is equal to VB final y. And we figured out the y component. So putting that all together, we know that the final velocity of ball B is just equal to 0. It stopped after this collision. So we have very quickly, in like 5 minutes, knowing that we can use conservation of momentum, looked at this collision and sorted out what's going on afterwards. This is one of the really powerful things of from momentum and conservation of momentum is collisions. This would have been very difficult to solve using, say, dynamics, right? We don't know the details of that force that's causing ball A to accelerate and change direction, or ball B to accelerate and stop. We don't know any of those details. So it would have been really hard for us to sort of model and sort that out. Likewise, we don't know the energy transfers that are going on in there. We don't know if those balls are dented or deformed and there's some sort of thermal energy increase or anything like that. So using just conservation of energy would have been very difficult. But with collisions, we generally can always use conservation of momentum. And if you define your system appropriately, that conservation of momentum is always going to hold in collisions. Next lecture, we're going to go through some more situations where, although that's true, we have to use conservation of momentum. We need other sort of ingredients to help us fully figure out what we need to know. But we'll put that off till the next video. For now, if there's any questions, email me. We'll talk about this more in our synchronous sessions and hopefully really start to get comfortable with it.